Okay, little explanation video then for this particular system. It's a friction play system, and we are going to draw the static behavior graph. Now, the first thing that we have to keep in mind is that this part is the one that we are interested in. So this is the point basically that we will be plotting on our graph. And also we are going to slowly increase the force first to the friction force of the mass. You can imagine there is a mass, there is a force going down, and that means that there also is a friction force. And initially it is of course pointed against the direction that we are pushing. As we are changing these directions, of course the friction force will also go in the opposite direction. So let's take a look at what we go. The first thing is that we have zero force, and then we go to we apply a little bit of force. First thing, of course, is the play moves into the right direction. So basically, we go over here from 0 to over here, and this is the first part. It's basically delta. Delta over 1. Oh, sorry, over 2. Half of the play, as it were. Alright, next up, now the spring K1 starts to come and play a part. So it now goes up with K1. It does that until the friction force over here is overcome. Because yeah, you can imagine it of course it doesn't have a friction force when it hasn't been pulled on, but as the force increases, friction force increases, and once this force is greater than this force, it will start moving. And what will happen then? First, the second play will come into account. So this is now play 2 over 2, half of it, right? Alright, next up, now basically all the play is out of the system. We've pushed this one inwards and that one inwards. So now K1 and K2, they're basically working together. Because they are in series, you have to add them up as follows. 1 over K1 plus 1 over K2. Now I don't really know anything about these values. I mean, sure, you can figure out. What I do know though is that it is less steep than one single spring, because they are in series, they are now working in series. That means that the slope will be more shallow. So we will now increase basically the force until 3 times the friction force, 1, 2, 3, with now basically a combined spring stiffness K1, 2. Alright. That was the easy part, as it were. Now we are going to go back. Now what we should know is that we have this mass, and at this moment in time, we've got displacement. See, we got displacement over here. Okay, because this is of course a displacement graph, F over displacement. And if you have a spring and if you have displacement, that means there is a force. That there is a force both in K2 and there is a force both in K1. Now this is basically what that equilibrium looks like right now. We are pulling on it, we have a force, 3 times friction force pulling on it, and on the other hand we have the spring force K2 pulling it back, but also the friction force is pulling in the opposite direction. So first, when we are going to decrease the force of the K1 basically. First, we are going to go down once the friction force. Now there is basically no friction force because this one is equal to this one, so there is no friction force anymore. Then we go down once more the friction force, and yeah, sorry, I cannot erase this, but there we go. Now the friction force starts to move in the other direction, and that is giving us something interesting. because now when it is the other direction, it will start moving. However, we are still in the right place. There is still displacement, so this force is still pulling on it, just not as hard as the other one is. So now the other one is pulling more than K1. So the whole mass is now shifting back. Now, there is still force on these plays, so the play will not be overcome, not until we hit the 0 point. So near there's 0 newtons on my graph. Now, of course, here it goes down with K12 again. This was K1. So when I have 0 force on this on this mass, what will happen? Well, of course, this mass, you can imagine, it is shifted a little bit to the right. See? And because of the friction force, it is now, yeah, basically over here. Why doesn't it go back? There is a spring that is pulling on it. It's trying to pull back, but there's also friction in this direction, in the other direction, in this particular situation. So even though we're not pulling on it, the whole mass has shifted a little bit to the right. And yeah, basically there's an equilibrium where K2 is almost equaling the friction force. Why do I say almost? Because it is not moving, it is static at this moment. So they are equal to one another, but yeah, probably the friction force is like 0.01% bigger than the pulling force, therefore it is not moving. So what we see over here right now, first the play is going to go opposite. So there we go. This is the play of 1 in the opposite direction. Alright, as I said, mass 1 is in equilibrium because it's a friction force pulling in to the right, and we've got K2 pulling the mass to the left. So I do not have to first go down to the friction force for this mass to start moving. I just have to very gently push it, and because K2 is already pulling on this block, it will go down. So K1 and K2, they're working together, and they're going down with this slope, of course. Again, K1, 2. Now, when we are at this point, now the basically the friction force has been overcome and it has been reversed, and now we get the delta 2. There we go. So this is now the second play. It's now being reversed, and in the second part we go down with slope K12 again, because now both springs, you can imagine, this is now pushing in the opposite direction. The spring 1, K1, is being contracted. This one is also being, sorry, not contracted, I mean compressed. Both are being compressed, so they're working together. That's why it's K12. Now we go up again with, because we are stopping the pushing. I'm slowly reducing the pushing force. So first we have K1, once the friction force, twice friction force. Exactly the same story as what we were talking about over here. Once the friction force has been reversed, we go back with K12 again. This was just K1 until it's 0. Now, when it's 0, first the play has to be reversed. There we go, play 1. And then we are going to pull up again, both with K12. And the final thing is when we hit the friction force again, it's reversed for the last time, we go to that displacement, and now basically this is delta 1. So yeah, my graph might not be like perfectly how you call it, dimensioned, but you get the gist, huh? I think the most important thing in this particular exercise is to imagine that over here in this point, when the friction force is being over 1, K2 is still extended, so it is pulling on our block as we speak. We don't first have to overcome friction for the mass to start moving, because there is already an equilibrium. So hopefully this was a bit clearer, and now you know how to draw a graph like this. Yeah, I wish you the best of luck at trying it yourself.